Moja Global started in 2013 in Kenya. Our primary focus is to foster collaboration on land monitoring systems that can aid countries in developing, implementing, and tracking policies and programs to reduce greenhouse gas emissions and improve land management. The land sector is one of the leading contributors to anthropogenic greenhouse gas emissions. Tracking emissions in the land sector and measurement, reporting, and verification requires tools like the FLINT. FLINT stands for Full Lands Integration Tool. The FLINT is an open-source integration tool that for the first time gives countries the ability to build and run advanced MRV systems quickly and efficiently. FLINT works by bringing together multiple streams of data. Imagine you have country X and you want to know how much carbon is absorbed or released by the landscape. The most important data is the land cover maps for several years. For example, one map each year, or one map every 2 or 3 years. Imagine we have 10 maps, every 2 years between the year 2000 and 2019. Now we put the maps precisely on top of the next, so each geographic point of each map ends on top of the same point of the previous and the next map. We can create a time series, a history of land cover change by drilling through all the maps for each designated point marked. The size of one point can be chosen by the user. It can be 1 hectare, or it can be 1 pixel on a satellite image. Let's imagine we use pixels for our calculations. So now, instead of maps, we have many stacks of 10 pixels starting in 2000 and ending in 2019. Let's look how FLINT deals with one stack. Let's say that on top of the stack is the pixel of 2000, and it is marked as forest. The next pixel is from 2001, and it is also marked forest. So from 2000 to 2001, the forest has grown on that pixel. But by how much? FLINT uses other sources of data to determine how much the above-ground biomass of the forest has grown. There are many possibilities. The easiest solution is that the user has precise information about the type of forest and the growth rate. This growth formula can be called a model. The model might use a formula that calculates growth rate on the basis of average weather information or on the soil type. In that case, FLINT will look up the information in its datasets for that particular pixel. All this information is then combined, and the growth rate will determine how much carbon dioxide has gone from the atmosphere to the above-ground biomass. If this specific data and model is not available, it is possible to find the location of the pixel on an eco-climatological map and use a global average growth rate for that particular zone. There are various other solutions, but the key is that FLINT will integrate the land cover data with other sources of information to get the most accurate result for the growth rate. And that FLINT is flexible enough to use the data that is available now, but can upgrade to another way of calculation when better data or models are available. The actual growth models can be Tier 1 or 2 emissions factors, or they can be advanced Tier 3 models. In all cases, FLINT works with alignment with the IPCC guidelines. So now we know how much of the above-ground biomass of the forest on the pixel has grown that year. We now know the amount of carbon dioxide that has been taken out of the atmosphere pool and moved to the vegetation pool. But the IPCC has defined 5 different pools in which carbon is stored. When using Tier 1 or Tier 2 emission factors, the changes to the IPCC pools are based on the standard factors, for example, eco-climatological zone. When using Tier 3 growth models, we know how much carbon has gone to vegetation, but we do not know whether we should put this amount of carbon sequestered into the above-ground biomass pool or the below-ground biomass pool. When using Tier 3 models, FLINT manages all the carbon pools to ensure mass balance. This basically means that carbon cannot disappear. It has to go somewhere. FLINT makes sure that no carbon is lost and no carbon is invented out of thin air by always moving carbon from one pool to another one. Like in double entry accounting, values always have a source and a destination pool. Using mass balance methods can increase accuracy considerably. The IPCC pools are the highest in the hierarchy of pools that can be defined by the user. In many cases, it may be desirable to have further subpools. For example, it may be necessary to subdivide the above-ground biomass into stemwood and other components, such as bark, branches, and leaves. This is particularly useful when looking to estimate carbon in wood products or emissions from forest fires. The FLINT system is flexible and allows for these splits in pools to be easily added as needed. To know whether the carbon goes to the above ground or the below ground pool, FLINT will use another formula. This could be a default root-shoot ratio or a specific ratio. Again, it is possible to start simple and approximately. Each time when better information is available, the system can be upgraded so it becomes progressively more accurate. How do we know how much carbon goes into the dead organic matter and soil? This can be done simply using emissions factors, but these are of limited use in many cases. So when more advanced models are used, the dead organic matter comes from vegetation. Trees fall over, leaves fall off the tree, twig break off, for example. This process is called turnover. Luckily, scientists have documented for many vegetation types how much turnover takes place annually or monthly for many forest types. Depending on the formula one uses, one needs to know how much of the biomass is in the leaves, the twigs, the stem. So using the pools defined by the IPCC will not allow us to calculate turnover easily. So FLINT allows the user to divide the IPCC pools into any number of subpools to allow for more sophisticated models. So let's say that now we have a pool for leaves, a pool for twigs, small roots, and for big roots, for stems and for branches. FLINT will run the turnover model to know how much carbon to move from the leaves, the twigs, or other pools to the dead organic matter pool. Dead organic matter will rot away. Also, for this process, models exist, for example, decomposition models. Depending on the model used, the user will again have to define additional pools, such as fast decomposing material and slow decomposing material. Each pool will get carbon put into them by the turnover models. The decomposition model will then take carbon out of these pools and put them into the soil carbon pool or move them back to the atmosphere. This is the way FLINT deals with regular growth of the vegetation. But there are many other events happening on the pixel of land we are looking at. For example, it is possible that trees were harvested and turned into wood products, or that a fire occurred, or that the land was grazed or fertilizer applied. All these events will cause carbon to move from some pools to other pools. Again, FLINT will use models to calculate how much carbon needs to move, and then FLINT will move the carbon between the relevant pools. If the models to calculate the shifts in carbon do not exist, it is possible to develop these models and attach them to FLINT. When all the growth and events have been taken into account for that year, FLINT will store all the changes and the final values of carbon in the pool in a database. The output database contains the carbon stocks of each pool and the shifts of carbon between each pool for every time step in each pixel. In the example, we have used annual time steps, but it is possible to use monthly or even daily time steps if required. So imagine that there are 20 pools. Every year, the values of every pool and the shift between pools are recorded. 20 possible shifts, requiring several terabytes to store. Luckily, not all pools can move or receive carbon to all other pools. Still, one can see that the size of the database can become very big if all the shifts are recorded for every month over 20 years. This output database can be used for all reporting. Different reports follow different policy rules. For example, the UNFCCC might require different land use classifications than the Forest Carbon Partnership Facility. Since the same output database is used for all reports, but different policy rules are then applied, all reports will be consistent. There is also a shift for many countries from international reporting to national reporting for carbon trading, adaptation, and policy development. Having one database from which these values can be obtained will not only reduce the duplication, now many countries are recalculating their emissions for each report they produce, it will also increase consistency between reports over time. Finally, and most importantly, it will free up time for government officials to improve the FLINT system continuously over time. As indicated, FLINT is flexible and can work with the data that is available. Since there is less duplication, more time and resources are available for improving the system. But where to start? Because everything can be improved. The user can apply the uncertainty model to identify which improvement to the system has the smallest cost or effort with the biggest impact on the accuracy of the results. This approach allows for the prioritization of the possible improvements. Measuring systems for the land sector are complex as they contain interrelated entities. As indicated in the latest IPCC report, the best approach is to use regular improvement cycles and learning by doing. FLINT provides the ideal framework for this type of continuous improvement. FLINT defines how the pieces fit together, while each piece can be improved and replaced each cycle. This allows for rapid improvement of accuracy, but it also provides for a structure to coordinate between different teams, possibly from different departments, that need to provide input in the form of data or research. Since FLINT is open source, users can improve the software so it better responds to their needs. With the FLINT, countries can develop policies for land-based climate change mitigation activities and produce both national and international reports like the BUR, NDC, NC, FREL and RED reports to different international organizations.